Okay, so I think the course is it's starting to get interesting. Like last time we looked at continuous functions, and we're slowly building up a nice set of examples. So when you're thinking about topology, the theorems are important, but also examples and counterexamples are important. And so you've got to build up like a bank of examples that you can use to test out ideas to see whether it's true or not. So you should always be thinking of, well, what does this mean for constant functions? What does this mean for the discrete topology, the indiscrete topology? Those topologies on R, like the half-open one given from the half-open intervals and that. They're good sources of counterexamples. And another really good source of counterexamples is anything to do with infinity, right? Because infinity, a lot of counterexamples come to there because things that are true for finite is not going to be true for infinite, right? So it's possible to, like you have an infinite sum of things, and you can factor out an infinite sum and be left with an infinite sum, or you could be left with nothing, or you could be left with anything in between. So, so that comes to products, what we're going to do to talk about today. So have you done much with infinite products? Okay. So, well, let's talk first about how you would construct a product in general. So we've already talked about the product topology on X cross Y when we've got two spaces. What happens if we've got an arbitrary number of spaces? Okay, so first you have to index your spaces, and so kind of so you need some index set. So you define a J tuple. So if J is an index set, a J tuple is just a function from J to X. If J is infinite, that's going to give you sort of interesting things, and you might want to put further restrictions on it. So, for example, you might be thinking of functions that have got finite support. So, for example, if X has like some special element like a 0, you might want most of them to go to 0 and only finitely many to be non-zero, for example. Or maybe countably, you can play things with finiteness and countability. So you might want to play around with J, and that provides interesting examples too. Okay, so alpha is going to be a generic, it's going to be like I for us. It's an element of J, and so X is a function, so X evaluated at alpha, sometimes we call that just X sub alpha. And that's the alpha coordinate of X. Okay. And so sometimes instead of using the function X, we'll write it like this, looking more like what we think a tuple should look like. So we're thinking of this as some sort of stream, although of course J could be uncountable, so might not just be a sequence, it could be anything. Okay, and if we look at the set of all J tuples of X, we usually call that X to the J. The one that you're used to is if J is finite, then typically what we use is a section of the positive integers like 1 through n, and instead of having a set 1 through n, we just call that n. That's what you're used to. Okay, so then once we've got this set of J tuples, then we define the Cartesian product to be the set of those J tuples. So you can think of this as a tuple and X alpha in A alpha for each alpha. Okay. Quite often it gets kind of annoying having to put the J in all the time. So we just think of this as we drop the use of J when there's only one index set there. We know what the index set is. So this is the Cartesian product, and that's a general element, some sort of J tuple. Okay, so great. That gives us an underlying set. And that's the first thing we need for a topology or for any mathematical structure. Okay, so now we've got a Cartesian product and we want to put some sort of mathematical structure on it. In our case, we want to do topology. Now, there are two ways to go based on our discussion on X cross Y. So remember, there was a basis and there was a sub-basis. So the basis came by the definition. So the basis is it's just collection of all the sets U cross V, where U is open in X and V is open in Y. Okay, so that gives us one way to think about a basis for our product topology, and obviously we can generalize that to a basis is then going to be sets to the form product of U alphas, where each of the U alphas is open in our space, X alpha. That's kind of the definition. But there was also that theorem 15.2, which came up with the idea of a sub-basis, which was that the collection pi inverse of U, such that U is open in X, union with that. And we can generalize that just to be the union of all the pi inverses of U alphas for any open U alpha in any X alpha. Okay. Now, they're the same thing in X cross Y, and they're going to be the same thing for any finite Cartesian product. But do you see why it's going to make a difference when it's infinite? Why is that? Well, why is it different? Well, what's pi 1 inverse of U going to equal in this? It's going to equal U cross Y. This is going to equal X cross V. So when you just take the inverse image of an open set, there's the open set in its alphath place, and the rest of the space is going to be the full topological. It's going to be the X alphas for all the things, right? And so then when you look at what that generates, right, you're only doing finite intersections. So your open sets are only going to be in a finitely many places. Is it not going to be the whole space? Right. So that this is this infinite. This is where infinity kind of screws you up a lot of the time. So these two things actually turn out to be different. So let's. So that's what I was talking about. So we can generalize these to any index set by just just taking the product of open sets or the union of all those inverse images of open sets, and they give rise to different topologies when we've got infinite sets. And this actually happens all the time in math, like not only for topology, but like for groups, vector spaces, like say you've got Z, the integers, and you take an infinite Cartesian product. One way to do it would be that you're allowed any integer whatsoever in any place. That gives you one Cartesian product. Another Cartesian product says that, well, only finitely many places is it allowed not to be 0. And if you think about it, that's also going to give you a group, right? Because if it's only got finite support, you add two elements together, it's only going to have finite support. The inverse is going to have finite support, etc. So they're two different kind of structures, and in a lot of cases, the one where you've got restrictions is more useful, right? So think of an infinite vector space, or think of the element, the infinite vector, which is like 1 in every place. What is its length? Well, it's going to be infinite, right? And so that might be, for whatever purposes you're doing, that might be, not going to be useful to you. So you're only going to be interested in vectors which have finite length. And of course, that's also going to be a vector space. So, but they're kind of like, this happens all the time where you have these different kind of products, and because of infinity, you want to put further restriction on it so that things are able to be used. Okay, so let's look at these two different topologies. The first is called the box topology. So again, okay, so we're setting up a Cartesian product. So we set up with an index family of topological spaces. So right, so we've got a whole bunch of X alphas. Each one is a set with its own topology. Although quite often we want the set to be the same. So it's like X to the J. But anyway, so to do a topology, we're just going to say what a basis is. And it's just going to be the collection of all sets of the form product of U alphas, where each U alpha is open in X alpha. And that would be like your first guess as to what would be the topology would be. And this is the box topology. Notice it's not called the product topology, because this is the one that we don't really use that much. So why is it a basis, first of all? Well, remember there's two criterion that you've got to have for a basis. One is that every element belongs to some basis element. Well, the whole space itself is a basis element because each X alpha is open in X alpha. So this is in our collection. So that's the first condition checked. And what's the second condition? The second condition is that the intersection of any two basis elements is a basis element. And then that's just like the product of U alpha intersected the product of V alphas, right? Oh, that's just the product of U alpha intersected V alpha. And so since the U alpha and V alphas are open, the intersection of U alpha and V alpha are open. So that's a basis element. So very trivially, this is a basis, and it gives us a topology. The other topology, which we call the product topology, so that's big warning signs that this is a big alarm, that this is the one that we're really interested in, is, well, first, let's define the projection map as just like what we saw before. So it goes from the whole Cartesian product to a particular space, and it's just the projection onto onto the bth element. Okay. So let S sub beta be the collection of inverse images under the projection map of the open sets in, oops, that should be an XB, of course. Right, so what does that look like? It's going to look like an infinite product where most of them are going to be X alphas, except an X beta, and an X beta, you're going to have U beta as the space. And then let just S denote the union of all those particular collections. And we're going to let this be the subbasis for our product topology. Okay? We call it the product topology. And in this topology, the Cartesian product is called the product space.
So that this first S sub beta, that is in the second half of its definition, that is all open sets in a fixed X sub beta.
Right. So that's just in the beta spot. Okay. So yeah, I thought about how to write that down. So you're tempted to write product of alpha not equal to beta X alpha cross U beta. And it kind of is. It would be homeomorphic to that, right? Because when I do it like this, I'm sort of saying putting the beta at the end. Whereas the whole point of an index set is, it's, like it's the nth coordinate, so it's got a place inside the thing. So when I write it like this, I'm kind of putting the beta coordinate at the end, when it really isn't. And typically, it's somewhere jumbled up there in the middle. So it's kind of like this, but that's not actually correct. So probably the best way to write it would be U alpha, right? Where U alpha equals X alpha if alpha doesn't equal beta, and U alpha equals U beta when alpha equals beta. That's probably a more correct way of writing it down. Because then because the order might be important for some reason. Okay. So this is a sub-basis, so it generates a basis. So if we let beta be the basis generated by script F, what do we get? So what we're going to get is it's going to be finite intersections of elements of this. So so what does an intersection look like? Well, if it's in the same S beta, you're not going to get very much interesting, right? Because if you've got pi inverse beta U beta intersected pi inverse beta of v beta, you're just going to get pi inverse beta of u beta intersected v beta. Nothing very interesting, but if they're in different things, so if we've got like pi inverse of alpha u beta intersected, alpha, sorry, intersected pi inverse beta of u beta, right? If this would be u alpha cross u beta cross, well, I did this wrong, right? Because I'm giving them the first places in the set. So this would be true if this is a 1. And this was a 2, for instance. I get that cross and then all the other u alphas. So what I would actually get doing the notation that I had before would be the product of alpha and j of u. Let's put back the alphas. Okay, I'm already getting myself into trouble because I can't use alpha, can't use beta, so I have to use gamma. Gamma and j of u gamma, where u gamma equals u alpha, u beta, or x gamma, right? If alpha equals gamma, if beta equals gamma, and if gamma doesn't equal alpha or beta. So you can see how it's very easy to get kind of like some sort of index psychosis or something developing from here where you it's very hard to actually write things down. But in general, what's the typical element going to look like? The typical element is going to look like some product of u alpha, alpha in j, where u alpha equals x alpha, except for finitely many alpha. So that's what a typical element is going to look like. So you can just keep on intersecting, but since it's only finite intersections only in finitely many places, are you not going to get the whole space in the product? Okay, so we've basically already proved the important theorem, which just compares the two topology. Okay, so the box topology has a basis all sets of the form product of u alpha, where u alpha is open in x alpha. That was just by definition. And our little calculation there said the product topology has a basis of the form product of u alpha, where it's open, and u alpha equals x alpha except for finitely many values of alpha. So you see from this theorem that for finite products, the two topologies are exactly the same. For infinite products, the box topology is in general finer than the product topology. Why do I have to say put in general? In what perverse cases does the box topology equal the product topology?
They're equal for finite problems.
Yeah, but I'm talking for infinite.
It doesn't, it's strictly contains for
No. Can you think of one?
Oh, does it have to be uncountable?
No, like I think if we're talking about the indiscrete topology.
Okay, with a countable product?
With any, yeah, with a countable product, with any kind of product, right? Because in the indiscrete topology, the only open sets is the whole thing.
So,
right, so trivially.
Except for finitely many except for 0. Okay.
So, and if it's the empty, well, except for the empty set, and if you've got the empty set in it, then we've got the whole thing is the empty set. So if it's the indiscrete topology, then the only open set is the empty set, or so the Cartesian product of the indiscrete topology, the open sets are either the empty set or the whole set.
So we don't even have, we can't
restrict it to one
we
thing.
can't say enough to say strictly contains in any given scanner.
Yeah. So anyway, so that's just one of the annoying things. But in general, that's not going to be a case. So again, in general, so typically we prefer the product topology to the box topology. And so if you were just given a Cartesian product of topological spaces, you can assume that it has the product topology unless it's stated otherwise. Now, why do we say in general? Why is that preferred? So we'll actually, the last theorem we'll discuss in this section, I don't know if we'll have time to do it. Oh yeah, good. Well, it's actually going to give you a good reason why. But what typically happens is that theorems that are true for finite products typically hold true in the product topology with the infinite. And there's a lot of theorems which is true for finite and it has no chance in the box topology. So just, so for example, the last theorem we're going to look at today, which says that a function, from the product topology is continuous if and only if its coordinate functions are continuous. That's a kind of theorem that you want. That's not true for the box topology, but it is true for the product. So the product topology just tends to be the one that it's used. Okay, so first let's look at a whole bunch of what I call expected theorems, which are true for both the box topology and the product topology. Okay, so suppose that on each space you're given a basis for each space. The collection of all sets of the form product of basis elements will serve as a basis for the box topology. And for the product topology, a basis for that would be, well, you take a basis element from B alpha, but it's only allowed not to be the whole space for finitely many. And that serves as a base. So that, if you look at that, that should make total sense. That's what you expect. And why is that true? The proof, remember, follows lemma 13.2. Which tells you that a collection is a basis that if, what do you want to show? So 13.2, remember, told us that for any open set U and an element of U, then there exists a C from your collection such that X is contained in C and it's contained in our open set. So that's the standard way that you prove that something is a basis. Okay, so let's use that. So let's say we're going to have to put it in product terms. So here's our typical element, a typical tuple, and let's just say it's an element in some typical open set. So if we're in the box topology, then this is, all the U alphas can be different for all things, but if it's in the product topology, then it's only going to be different in finitely many places. So we're not going to use the difference between the box topology and the product topology. This is why this thing works for both. So what do we need to do? We need to show that that this is true. So this is what we need to show. And this is true. This is true because this is a basis for each X alpha. And so in each coordinate, it's true that X alpha is an element of B alpha in each coordinate. So that actually works. So it's actually.
So we're only considering the product of open sets, or what's the?
Yep. So these are open sets.
Okay.
U alpha open, with the caveat, of course, that if we're dealing with the product topology, only finitely many are not equal to the whole set.
But there are open sets in there that look different than that, right there?
Yep. They could be. Yep. So this is an arbitrary open set, right? So if it's in the box topology, it could be different everywhere, but in the product topology, it's only finite in many places. Is it not open to the whole set? So I mean, but nowhere here are we using infinity or finiteness in each of these sets. I mean, it's true that this is an element of the product because in each coordinate this is true. So this is useful theorem. This is actually a useful theorem. So for example, if we consider returning now to finite topologies, finite products, just consider Rn. What's going to be a topology for this? Well, a according to this theorem, all we've got to do is we can use a basis for each component. And each component is just R, and so a basis in R is just the open intervals. So Rn has basis any open prism. So anything like A1, A1, B1 cross A2, B2 cross AN, BN. So that's just some sort of open prism that's in Rn. And so that gives us a basis, and we call that the topology that it gives, that's the standard topology for Rn. Okay. And you can even, and even tells us, it even gives us a topology for an infinite space, right? So Z plus, I guess we could call that our omega. Okay, so in the box topology, it's any infinite prism, whereas in the product topology, it's only finitely many open intervals. All the rest is the entire R. So, for example, something like 1, 2 cross R would be an example of a basis element in the product topology. Okay. What's the next one? So how do subspaces work? So let's say for each space X alpha, we have a subspace A alpha. Then if we take the product here, that's going to be a subspace of X alpha in the relevant topology. So if both products are the box topology, the subspace of that, and if both are a product topology, that is a subspace of that. That's kind of how we expect. That's going to be a homework problem for you, as is the next one. If each space X alpha is a Hausdorff space, then the Cartesian product is a Hausdorff space in both the box and the product topologies. And then finally, in both the product or box topology, then the product of the closures is equal to the closure of the products. Okay, so that's nice. So let's actually prove that one. Yep, you've got enough time for this. So again, I'll just do the proof, and in nowhere do we assume that we're in the box topology or the product topology. So the proof works for both. Okay. So let's assume, let's go this way. So let's say that X is in the product of the closures. And of course, the general element looks like a tuple. Okay, and let U equal the product of open sets. Let that be a basis element containing X alpha. Okay, so if it's in the box topology, the U alphas can be all different, and if it's in the product topology, only finitely many are not different from the whole thing. X alpha be in the product. So that means that each X alpha is contained within the closure of A alpha. So that means there exists a Y alpha, which is in U alpha intersected A alpha. So that's true for each alpha. And so that has to be true for each thing. And so we just consider Y alpha. And that is an element of U intersected with the product of the A alphas. And so that tells us then that X alpha is in that closure. So it meets that point. Okay. What about the other direction? Let's say we're given an element of the closure of that product. And so let V beta be an open set of X beta containing the element X beta. Okay, so if we look at its inverse image, that is open in the product space, and that's true in both the product and the box topology, right? It's true in the it's true in the product topology, so therefore it has to be true in the box topology as well, because the box topology is finite. Then the product topology. So that means this set here contains Y alpha. Of So there has to exist some element then that's in there. And so y beta is an element then of v beta intersected a beta. And so that tells us that x beta is in the closure of the individual space.
What was x beta?
X beta is just the beta term of this. So this is, so what we did, so here we've got an element that is in the product of each closure. And so we show that that element was in the closure of the whole space. And then if we've got an element which is in the closure of the whole space, we've got to show that its coordinate is in the closure of each coordinate space. Okay, now, so that's all good and all well and good, but now we've got something where we've got something unexpected happening. And this is something that we really want to happen because, you know, this is a basic fact about continuous functions that we kind of need to be able to kind of deal with it. And that is, so if we have a function from some set into the Cartesian product, where each so each coordinate, we've got a coordinate function. Then only in the product topology is it true that f, the whole function, is continuous if and only if each coordinate function is continuous. Now, remember, functions that go from the product to another space, there's no good criterion for this. So this is as much, because we saw that in the case of r squared, for instance, from r to r squared. And that this theorem fails in the box topology. And I think I'm going to have to leave it on a cliffhanger. We'll finish this off on Friday. The proof is actually quite straightforward. The counter example to show why it fails in the box topology is kind of sneaky. So I want to have time to